So the first presenter today is Brian Lawless. So Brian, without further ado, take it away. Thank you.
Wait, sorry, Brian, can I cut it? I'm going to be the little sign person back here.
All right.
All right, well, welcome everybody. My name is Brian Lawless, and I'm here to present my research that I did for my master's, and it's called the Use of Photochemical Reflectance Index to Predict Soil Moisture. Now, I promise this is going to get more interesting than the title belays. There's actually going to be some audience participation today, but the presentation actually relies on the sensor that you see here in this picture, which is called a spectral reflectance sensor, and it was actually developed, the prototype was, by our own Lee right here at U of I. So it's kind of cool to be able to use that. My original research question was, can remote sensing be used to detect plant changes that are induced by climate change? So to understand the question, I'm going to break this down into three parts: climate change, plant function, and the new remote sensing technology. So starting with climate change, what we're talking about is the IPCC predicts that over the next century, the planet's going to warm. And some areas will become drier, and some areas will actually become wetter. And since temperature and precipitation are two of the primary driving factors in plant growth, it makes sense that policymakers, scientists, land managers would all want some tool to be able to ascertain the impacts. And so what we're looking at when we talk about plant function is specifically photosynthesis. How well are these plants taking sunlight and carbon and turning it into energy? So we know that when plants experience drought, photosynthesis is actually reduced, but those plants are still getting hit with sunlight. And that extra sunlight runs the risk of oxidation of the plant's tissues and permanent damage to the plant. So plants actually manage that extra energy through something called the xanthophyll cycle. Now, to help you understand the xanthophyll cycle, I've written a little bit of a song, and I'm going to need some of your help during this song. Now, in the song, when you hear me say the xanthophyll cycle, you all have to say xanthophyll. And you have to do it with energy, and you have to do it with passion. So we're going to practice one time. The xanthophyll cycle. Xanthophyll. That's very good. All right, we're going to see how well this whole thing works. And a 2, 3, 4. Say you're living out in the woods, you got water and sunlight, life is good and everything goes just like it should. You spend your days on good hard quick, but if the water on tap is at your place, so they can put your plants in a terrible state. Well, if they don't have water, they still have life. Your poor old plants might oxidize. Well, they got a great trick and it's really sweet. They don't energy in the form of heat. Don't you worry and don't dismay. The xanthophyll cycle's here to save the day. The xanthophyll cycle. The xanthophyll cycle. The xanthophyll cycle. The xanthophyll cycle. Well, the sun tries to get them, but it never will. Well, thanks to our new friends like the the old xanthophyll is the intermediate state. It's what we see when things play, but as the summer runs on and the season's late, the old xanthophyll must deoxidate, and there's xanthophyll. The intermediate state, but say a xanthophyll really takes the stage in the xanthophyll cycle. Xanthophyll. The xanthophyll cycle. Xanthophyll. The xanthophyll cycle. Xanthophyll. The xanthophyll cycle. Xanthophyll. Well, don't you worry and don't dismay. The xanthophyll cycle. One more time. The xanthophyll cycle. Xanthophyll. The xanthophyll cycle. Xanthophyll. The xanthophyll cycle. The xanthophyll cycle. Well, don't you worry and don't dismay. The xanthophyll cycle's gonna save the day. Don't you worry and don't dismay. The xanthophyll cycle's gonna save the day. The sun tries to get them, but it never will. Oh, thanks to our good friend, xanthophyll. Oh. All right. So, now that ridiculousness is over, hopefully you understand the xanthophyll cycle, and you'll walk around campus singing the xanthophyll cycle song, making people wonder what exactly is wrong with the people at the College of Natural Resources. So, on to remote sensing, the last piece of the question. What we're looking at is optical remote sensing. In other words, looking at the sunlight that's reflected off of a plant. When sunlight hits a plant, one of 4 things can happen. It can go right through the plant like nothing happened. It can hit the plant and be absorbed for photosynthesis, sorry about our breath, which is a good thing. Then it can hit the plant, be used for oxidation, which is a bad thing, or it can bounce off. And that reflectance, that bouncing off, is what we're interested in, because when the xanthophyll cycle is active, that reflectance changes. So what we do is we look at 2 wavelengths of reflected light, the 570 and the 531. Now on this plot, the dark green line represents the reflectance off of a plant that's not under stress. The light green line represents what happens when a plant is stressed. And if you notice, the signal at 531 actually drops. So we take those 2 values and we record them, and we compare it to each other using this formula developed by John Gammon in the early 1990s, and we develop what's called the photochemical reflectance index, or PRI. Now, if you notice, if this 531 factor goes to 0, we end up with a -1. So the lower our PRI value, the more stressed out the plant is. So how did we do this? Well, what I did was I went out to the Noakes property outside of McCall, dug a bunch of big snow pits. Each of these pits had about 3 tons of snow in it, literally. And the idea was that these plots would represent our drought. So these would be plants that didn't get all of their snowfall because we removed it. We did this checkerboard pattern so that each plot would have 4 walls of snow around it to make sure that they all had any groundwater seepage was equal across all the plots. And in the middle, we put a pole with the PRI sensor up at the top and a soil moisture sensor buried 15 centimeters in the ground. And what we did was we compared that to some known metrics, namely biomass, which is the amount of plant material that grows throughout the season, and then the pre-dawn leaf water potential, which is a way of measuring how much water is actually in the plant. When they dry out, they don't want to let go of their water, which means they can't do photosynthesis, and that's sort of what starts the whole thing. So you notice there's a version 1.0 on here, and that's because we had a few problems. The first one was this. When the snow melted, the entire field flooded. So our whole wet versus dry concept was at risk, but I thought, hey, what I can do is come in later in the year and put water on the control plots, so they would continue to have water throughout the year, and then the other ones might dry out. Then we had a second problem. Cows ate my research. Oh no. So cows ate my research, and the reason that that's a bad thing is because it meant that we could not do our biomass testing because the cows ate the biomass. But Jan and I went out, we used the rock, we put all of those sensors back in the ground and moved on. The last problem was our dry and wet plants never experienced a dry versus wet difference. There was no statistical difference between the dry plots and the wet plots, so our whole pre-dawn leaf water potential thing couldn't be used either. So what do? Well, we rephased the question. And the new question was now, can we simply use PRI to predict soil moisture levels? And the paradigm here is that lower soil moisture leads to less photosynthesis, which leads to a higher xanthophyll response and a lower PRI. So that's how these two are connected. And what I did was I developed 10 different models, 10 different ways of testing that using linear regression. And the 10 models are all the values for PRI against their paired. VWC is volumetric water content. That's our soil moisture. So all the PRI values against their soil moisture, just the ones during the day, because at night there's no sunlight, so our reflectance values get a little wonky. Then we had solar noon, so when they get the maximum light energy. We had the value early in the day when they have plenty of water, but low energy, and then at the end of the day when they have low solar energy and hopefully, or theoretically, not much water. The second set of these involved taking the average of all of the soil moisture values for the day and creating a mean, and then looking for the lowest PRI value, the highest PRI value, the average of all of the PRI values, then the standard deviation, which is a measure of the spread of the data, and then finally the cumulative PRI value, which is the equivalent of integrating the PRI throughout the day. Took all of those models, put them into R, and used RStudio to crunch all of the numbers and create all the graphs and produce our results. And here's what we got. This is all 10 models with their results. The dark green values indicate values that might show some sort of correlation. The 3 gray ones here are the 3 that match the most: the minimum value, the maximum value, and the standard deviation. So let's look at those 3 in detail. The minimum value did what a person would expect. As our soil moisture went down, our PRI value dropped. But this gray bar represents our 95% confidence interval, and you can see most of those points are outside. In fact, despite having some good values, our adjusted R squared is only 0.34, which means using this as a predictor of soil moisture isn't going to be such a great option because there's just so much variation. Same story with the mean daily value. You can see there's a lot of spread about the 95% confidence interval. We have the same trend of lower water content is lower PRI values. And again, a pretty low R squared of 0.35. And our final value was the standard deviation And this one was tricky because it didn't do what I expected. What I thought was, as the plant started to dry out, we would see more variety in the values during the day. But what we actually saw was, as the plants dried out, the variation narrowed. And that was kind of backwards, but as I think about it, my new hypothesis is if they're starting out at a lower value, there's less of a range that they can move through, and that's why those values are tighter. But that would be great for follow-up experiments to see if that's what's going on. We had a little bit better fit of a 0.41, but still a lot of variation. So basically, at the end of the day, what I think is going on is, even though the mean, the minimum, and the standard deviation show a relationship, that relationship is weak, and that makes it difficult to use it as a predictor of soil moisture. Part of that could be the way we measured soil moisture. So firstly, the volumetric water content might not be a good predictor of how much water the plants have in order to do photosynthesis. Secondly, we had our sensors I had my sensors at a depth of 15 centimeters, and that could have been too shallow or too deep to really get a picture of what water was available to those plants. We had a lot of grasses and stuff in the area we were at. So even though there is a connection and a relationship between the two, we need to understand a little bit better what's going on before we can use this as a predictive tool. And essentially, we need to know how precipitation affects soil moisture over the course of a season, and really what causes all that variation, because that variation isn't explained. And I think that's something we need to figure out, why we had so many values. So at the end here, I just want to give thanks to all the people that helped on this program. My wife, Tanette, for giving me the time and money to go do this whole thing. Jan for all of his phone calls and time there. America View for paying for my research assistantship. Decagon for providing thousands of dollars worth of equipment in order to do the experiments. The Harold and Oaks family for letting us use their property. Wes and Willie for letting me use their code. Marina for helping me shovel snow. All of my cohort for giving me the confidence to stand up here and be brave to do this. University of Idaho for making this possible, and of course the staff and faculty at Moss, without whom this adventure wouldn't be possible. So with that, I'd like to take any questions that you guys have. It's hard to breathe and be nervous at the same time. Questions? Really, I did that well? That is fantastic. I figured somebody in here would know about PRI. Yes?
What plants were you trying to measure?
So that's a really good question. What I thought the meadow was going to be full of was mostly grasses, sedges, and wildflowers. And then in the spring, I was surprised to see all of these corn lilies show up in there. So there was actually some variety. Some plots were dominated by these corn lilies in the early summer, but by the end of the year, they were all grasses, sedges, and wildflowers. Yes?
Did you see any noticeable change in PRI taking place as a result of that change in canopy cover?
So I didn't have really a change in the canopy cover because I was out in an open field. Oh, you mean as these guys
going from
disappeared.
like corn lily to grasses? And
I see what you're saying.
Yeah.
Actually, no, because these corn lilies would have been in the way of the grasses underneath, so they wouldn't have really functioned as a canopy. But I didn't pick that apart. That would be something else that somebody could do with the data, because I know which plots were dominated by corn lilies and which weren't. So that would be a good comparison to do. But I was really more interested in the end of the year when everything started to dry out.
Yeah.
Plus, cows pretty much destroyed all of this.
Right.
Yes,
Forgot
ma'am.
about that.
Did you lose your car keys at one point?
No, I didn't, but I did drop like occasionally a screw or something, and then you just couldn't find it. It was kind of a nightmare. But yeah, that was to give you guys something to look at while we were answering questions. Yes?
You think this tool is better for diurnal measurements or looking at seasonal changes of the canopies you're measuring?
That's a really good question, and I think that the data is pretty useless if you just came by and took one picture. So I think you need to be comparing it to previous values. So it's more of a seasonal value, but not in the sense that, oh, we just take a picture in the fall and now we know what's going on. You have to be recording it throughout the year and then comparing it to the values. And I don't think you could say from one day to the next, like, oh, today they're dry and tomorrow, yesterday they were wet. I think you need to look at, oh, hey, today's value relative to the average is too high or too low, so that tells me something's going on. It's really good for a trend tool right now. Anything else?
Good question.
Last question.
Do you have a way to determine how much green versus how much background soil or
So
dead plants?
that's a
or-
really good question, and I didn't go into this in the presentation. What Lee's asking is whether or not I had a way to separate just the reflections from the plants from the background. And I actually did use what's called a delta PRI value. So I took an early morning value, which would basically get a snapshot of what was going on without the sunlight reflecting off of it, and then subtracted that from the reflectance value. So I was basically taking that background noise out. So these values have all been normalized throughout the year. Yep. Okay, I think that's it. Thank you.
Well, you probably did half of our work for us to introduce the next speakers. So I'll turn it over to you.